So you guys in your journal can go ahead and label it benchmark review. All right. I will be using various slides. You can use as many pages as you want or as little pages as you want, whatever you got to do. Just a quick review from yesterday, okay? What did this graph represent? What kind of reaction did this graph represent? This was an exothermic. So what kind of H value did it get? Or delta H value or Q value? A negative, right? Okay. So this was an exothermic because it lost energy, all right? On this graph, there you go. What was this line? Gas. You have to count the 3. Okay, what was this temperature? 0 degrees Celsius. What was this temperature? You too. Okay, all right, good. Going from a solid to a gas, was this an endothermic or exothermic? Endothermic, that was the big thing. Good. All right, cool. Okay, so that's your little review from yesterday. All right, so next thing, we're going to start with gas laws. Okay? You didn't have to write that down because hopefully you still have those notes. These are the notes that some of y'all threw away. So, gas laws, we're going to start with that. Okay? Okay, so to start us off on gas laws, we're going to talk about your KMT. Does anyone remember what that stood for? Yes, kinetic molecular theory. And what was the big idea of the kinetic molecular theory? It was about particles are always what? Moving. Good. Particles are always moving. Are always in motion. Okay? But more specifically, this kinetic molecular theory talks about something called an ideal gas. Okay? And so an ideal gas is going to have these specific things about those particles that are always moving. All right? So now we're going to focus in on the gas part of it. So, those particles, do they travel in straight lines or do they curve all over the place? Straight lines only. And the thing that contributes to, I said it's particles, straight lines. They travel in straight lines. I'm sorry, I left out travel. All right. What that contributes to is that their collisions will be what? Do you guys remember? Elastic. Good. Okay. So no energy loss. Okay. Collisions are elastic. And that comes from them going in those straight lines. Okay, and just hitting. Kind of like billiard balls. Okay? All right. Their particle size. What was important about the particle size? Was it something that could be ignored, or was it something that we have to pay attention to?
No, not ignored.
We want to ignore it. I don't know if that's what she said. Okay. Particle size.
Ignored.
I'm going to put the fancy word up there, negligible. Okay? Negligible. All right? Meaning, if we can treat them like little specks, we will. Because we want a lot of volume of them, but those things should not have a volume that makes it significant about displacing space kind of thing. All right? So, all right. How about forces? Are there forces of repulsion and attraction, or do we want them to not be attracted and repelling? So a real gas, is there forces of attraction and repulsion? A real gas? Well, let's talk about a real gas first. Yes, right? Things are positive and negative. Do you guys agree? Up on the periodic table, things have positive charges, negative charges, so they're going to be repelling and attracting each other. But this ideal gas, this made-up imaginary one, no forces. Okay? And then finally, what is temperature relative to, or what is it representing for us? What is it? I think in the past we've said a measurement of, starts with a K. Yes, kinetic energy. And so what I've kind of told you guys to think of, so at the molecular level, is I want you to think of speed. It's the speed of those particles, okay? So we can directly relate temperature to whatever those things are doing, okay? Okay, once you have that, I'm going to turn it. All right. So the next thing I'm going to show you is a problem that we didn't necessarily go over exclusively. It's still one of the ones that we have done. It's just kind of in disguise, all right? So this is one where you have two vessels that are going to be connected kind of like that, okay? And so you have this little, I don't know, like a stopper in the middle, I guess you could say. And then this side is just full of gas, all right? And this side is not going to be full of gas. This side, they're going to say, is a vacuum, okay? So this little vacuum over here, what can you guys tell me about vacuum?
Has very low pressure.
Does it have any pressure, actually? Have you guys ever heard of space being a vacuum? Like vacuum? Okay. All right. So if space is a vacuum, is there anything in space? No, right? So this means there's zero pressure. So put 0 ATM. Okay? All right. But that whole side that has 0 ATM.
Is that one like really supposed to be?
All right. So the volume of this side is going to be 500 milliliters. Okay? This side over here, which is full of all the gas, this one is only 100 milliliters. Okay? And it has a pressure. Since there's gas in there, there has to be pressure in there. So it has to be some number. So we're going to say 15 ATMs, or atmospheres. All right? Okay, so the question is going to be asking you, what will the pressure be if stopper is opened? Okay? So what will the pressure be if the stopper is opened? So the whole idea here, the thing that I wanted you guys to be ready for is when you hear the word vacuum, you need to automatically know 0 ATM, all right? But let's look at what type of problem this actually is, okay? So we're going to throw that off to the side. All right, so we have 100 milliliters, 15 ATMs. What is 100 milliliters talking about? Volume, good. Okay, what is 15 ATMs talking about? Pressure, okay? So those two are what law? Boyle's law, exactly. Okay, so this is PV is equal to PV. And now we're just going to fill in. The part that makes it tricky is knowing what that second volume is going to be. So what I need you to think of is if you were to open this. So you have all this gas on one side. If I were to open it, where does that gas go? To the other side, right? It's just going to all just kind of spread out. And so it's just going to take up that entire container. Okay? So if the original pressure was only 15 ATMs and it was only in 0.1 liters, notice I changed it to liters for gas laws. Okay? We want to know what new pressure is going to be. What is the new volume?
600.
It is 600 milliliters. Do you guys see that? If you open that up, it's both compartments now. So it takes up the entire container, which will be 600 milliliters. So now, this you should be able to solve, right? Right here. Okay? Put that into your calculator, and you get 1.5, and you get equal to P times 0.600. We divide this guy over, you'll get P is equal to 2.5. So just write that example down so you have it ready, and then you guys will see which problem it is on your review. Okay? But this is one that it is still Boyle's law, so you've done this before in your life. but it's kind of like a hidden question because you got to know what vacuum means. You got to know what those little container things look like and all that stuff. Okay? Does that kind of make sense? Okay.
Wait, how do they make a container with 0 pressure?
Just suck it all up. Oh, they're funny. All right. So for this one, what I want you guys to write out is PV over NT. Is equal to PV over NT. All right. What law is that? This is your combined gas law. Okay. On this review, we're not really going to be asking you too much to memorize the names right now. Remember how I kind of told you back when we took that test? I said, as soon as you take this test, I don't really care. I mean, it's good to know the main ones, but if you don't remember, it's okay. What you do need to know, though, is the relationships. You still need to know these relationships. So I want everyone to rely on combined gas law to figure that out. Okay, so just a quick review. We have the PV. They're next to each other, right? So if we have PV equals PV. PV is a what relationship? Since they're next to each other. Indirect or inverse, okay? So one goes up, the other one goes down. These other ones, you have V over T. You have P over T. Gay-Lussac, right? We have V over N. Okay, what were all these? These were all direct relationships, meaning as one goes up, the other one goes up. So, if we were to ask you a question that said something about this pressure increasing as I put more stuff in, do you notice that that is not one of our laws that we learned? Did we ever learn about P over N? No. However, what can you tell me this relationship is? Direct or indirect? Which one does it look most like? It's a direct relationship. And that should make sense to you. If I had everybody piled into the corner and then I keep shoving more and more people and I just like stack them on top of you, there's going to be a lot of pressure, right? Yeah, so same idea, all right? But I just wanted you guys to know that you can rely on your combined gas law to know your different relationships. So don't forget you have that tool, okay? All right, a couple more things about general gas law stuff. So we have STP. What is STP? And there is no reason why this is next to it. I'm just trying to save space. Yeah, don't worry about it. Just put it wherever you need it. All right. So it is standard temperature pressure, which would include 1 ATM and 273 Kelvin. Okay. We also have the ideal gas law, which is PV equals nRT. Okay. PV equals nRT. Remember, when you are solving for a variable such as n, you leave it alone, move the other ones over. Okay? There you go. All right. Okay? We also had MW was equal to DRT over P, right? What was the MW standing for? Molar mass, right? Molecular weight, yes. It's molecular weight, you're fine. And then D was what? Density, which was what in disguise? Mass over volume, right? Okay. All right, so you had all those. What we're going to talk about, oh, in just a second, sorry, one more thing. One more little fact. I want you to make sure you understand a rigid versus flexible container. What's an example of a flexible container? A balloon, right? Okay. A rigid container, what would that be then? A glass. Good. Glass bottle is fine. Yep. So anything like made out of glass is a rigid container. So if I say you have such and such, all these things inside of a rigid container, what am I telling you is staying constant? Right. So volume is constant if I tell you a rigid container. You have to fill that in by me just saying that word. Okay? All right, now the next part is just the few ways that we solve our problems, and then we're moving on to acids and bases, and then you're done. Okay? So, we're ready? Okay. You can kind of put a line down the middle. You can say no balanced equation. And you can say balanced equation. So if you remember, we had two different types of questions that we were using with ideal gas law. When we had no balanced equation, we were using the idea that 1 mole is 22.4 liters. Okay? When we had our balanced equation, sometimes we used the liter bridge. Or we used stoic and ideal gas law. Okay? Those are the two main differences. So we're going to go through just the few equations, and then we'll be done with it. So when you don't have a balanced equation, you're always talking about the same one, because obviously there's no coefficients that you get to mess with. So this is when you will use either ideal gas law by itself, meow equals dirt over P by itself, or if they want you to go from grams of a gas to how many liters contain it, right? You can say grams, bring grams down, go to the mole. Mole comes down, go to the liter. So what this would be was 1 mole, molar mass, 1 mole, 22.4. Okay? And if we were doing the opposite, it would be the opposite. So you don't have to write it down unless you want to. But you would start with liters. Then you would come down and bring 22.4 liters to 1 mole. 1 mole comes down to the right, and you go to molar mass in grams. Okay? So this is if you're making So if you notice, this whole thing is conversions. Okay? These two have to be at STP for sure, though. 22.4 is specific to STP. Okay? Okay. All right. So for balanced equations, we had a liter to liter calculation. Okay? In this one, this is where you use the liter bridge. So we would start with the amount they gave us. We would bring that down and to the right and cross the bridge. So remember, this is where you use coefficients. Okay? Coefficients. So anytime you see this little bracket in my notes, that's going to be your coefficients. Okay? If we had a gram to liter, what do we start with? Stoichiometry or ideal gas law? Remember, ideal gas law goes wherever volume is. So do we start with stoichiometry or ideal gas law? Stoichiometry. So we would go from grams. We would say molar mass in grams to 1 mole. And then we would cross the mole bridge. And then whatever answer you end up getting is going to go into ideal gas law set equal to volume. Can I kind of get rid of that other side? There you go. That way I have room. Okay. Okay, so does this, you guys kind of remember that? And then the other one is going to be a liter to gram. So this one, we start with what? Ideal gas law. We're going to solve for N. So we're going to say PV over RT. And whatever we get from that, we start some stoichiometry. Bring it down to the right, cross the bridge. So coefficients. And then 1 mole to molar mass. And that's it. So that's it for gas laws. And then we're going to just do a small, tiny bit on acid base, and then you guys are going to start your review. So acids and bases. Fun stuff. So we got the pH scale. Let's start with that. Okay? It goes 0 to, what's in the middle? 7. What goes at the end? 14. That is a 7. There we go. All right. Which side of the pH scale is basic on? Everybody's like pointing this way. All right. The 7 to 14. There you go. Okay. So this is your basic side. This is your acidic side. And 7 is your neutral. Okay. Where water usually is. Okay. In terms of litmus paper, what color does acids turn? Red. And basic turns blue. Which one of these two reacts with metals right away and releases hydrogen gas? Acids, yep. So I'm gonna write metals next to it so that you know that's what it messes with. Remember, activity series is big on this. It bumps out the hydrogen. All right. Acidic things have hydrogen ions and hydronium. Can be written both ways. Sorry, that is a 3. There you go. Hydronium. Okay, so if you need to write that word out so that when you see it, you don't get confused. Okay, versus basic stuff has OH minus, which is called hydroxide. Okay, so especially on the review, I think I write them out and don't give you the actual symbol, so you need to be able to recognize what that is. Okay. Okay. Strong acids and bases. What makes them strong? They completely what? Dissociate. Good. Okay. Or completely ionize in solution, meaning they separate into the OH minuses and whatever metal they are with, and then the hydrogen goes away with all the anion, okay? So they completely dissociate if you're a strong acid base. This makes them a strong electrolyte. What does an electrolyte do? Does it conduct electricity or does it not? Electrolytes. That sounded like a guess. Yes. Strong electrolytes are going to conduct electricity, guys. This is the one where you guys had the little light thing with the battery pack and you put it into the different solutions and it lit up. So your strong acids and bases for sure are strong electrolytes. All right. Now, you had to memorize strong acids. What was the sentence we were supposed to memorize for strong acids? Good. I bring clay, not food. Ooh. Okay, because hydrofluoric acid is a weak acid. However, hydroiodic, hydrobromic, hydrochloric are all strong acids. And we had one other rule. 2 or more what? Not hydrogens, oxygens. So these are oxy acids, okay? Or oxoacids, sorry. 2 or more oxygens than hydrogens. So nitric acid, sulfuric acid, all of those. Okay? Your strong bases, what did we make on the periodic table? A B. Good. So it starts at lithium, goes down to cesium, over to barium, and up to calcium. Okay? Anytime those are attached to an OH, that is a strong base, and that's it. So if it is not found on any of these 2 lists, then it is not strong. Okay? Let's move that up so you guys can see it. There Okay? And I have one last thing after this, and then you're done. Yay! Is your little equation. So remember, 14 is equal to pH plus POH. KW, which was 1 times 10 to the negative 14, was equal to your concentration of H's times your concentration of OH's. And remember, the H plus can also always be hydronium, which is H3O. Okay? Then we had pH. pH was equal to a negative log of the concentration of hydrogen or hydronium. POH is negative log of hydroxide ions. Okay, by the way, brackets are molarity. Okay, or molar solutions. If they say 5 molar or 5M, okay, that's what they're talking about. All right, if I wanted to find the concentration, I could take 10 to the negative pH. If I wanted to find hydroxide concentration, I could do 10 to the negative POH. Okay? And that is all I've got for you. So now you're going to get your review and you're going to work on it.